Hello everyone, welcome back to the next edition of mathematics. Today we're going to explore a bit on second order ordinary differential equations. This is one of the requests by one of my students here. So I'll try my best to show the appropriate steps on how to solve a second order ordinary differential equation. Right? Now let's take a look at this. Okay, here we are given the variable y depends on x and the variable x and t are related by this equation here, x equal to exponential t. Right, we can see here. Now show that this first order differential equation is given as such, and then the second order is given as such. And then next, once we are able to prove this, then for the next section, we are going to um, transform. We're going to transform this section here into another differential equation that involve only t and y. Right? Now, once we have done that, we are going to evaluate the complementary function of the differential equations in t and y, and then we're going to rewrite this solution in this form here, where r and phi are arbitrary constant. And then number 3, we are going to find a particular integral of this differential equation in t and y. And then lastly, we're going to find the general solutions to this differential equation in x and y. Okay, now let's look at how to work with this. We're going to start with this equation first that is given here, x equal to e to the power t. Okay, now all we need to do is just differentiate this with respect to a t, first differentiation. All right, now that would give us et, of course, right? And then now et is also given as x, so we'll write that as x. There shouldn't be a problem here. And then next, we're going to maybe it's best if I rewrite this in this case. So we have dx dt equal to x. Okay, and then next we're going to further differentiate this to obtain the second order differentiation. All right. So the second order differentiations, or the second derivative d2y dx squared here. Right. Now to obtain the d2y dx squared, we need to get this equation first. Now before that, I'm going to label this as number 1, and then dy dx using chain rule. We know that dy dx is equal to dy dt divided by dx dt. Okay, now that's what we have. Okay, all we need to do now is we have our dx dt, which is a x. So I can actually rewrite this as dy dt divided by x in this case. And then next I can transform the x over to the other side. Therefore, I can conclude that my x dy dx is actually equal to dy dt. Alright, now I have managed to prove the first order differential equation. Okay, this is what I have right now. Okay, now next I'm going to further differentiate this. Okay, to do that I'm going to write it down here, it's easier. So I'm going to further differentiate this. With respect to x. Now I'm going to do that for both sides. Okay, so that's what we have currently. Now for this one, it shouldn't be a problem. That is just a second derivative. Oh, okay. I think I forgot to include my x here. Yeah, so maybe let me erase this. So the correct one would be I'm trying to differentiate this equation number 2 with respect to x. So I miss out my x here, so I just rewrite that. dy dt. Okay, so that's what we have. And then I need to apply a bit of product rules here. So that would be dy dx plus x d2y dx squared. Right. Now this is the one that you need to remember how to differentiate this implicitly. So if I were to differentiate this, it should be d2y dt squared multiplied with dt dx here. And then I know that dt dx is actually 1 over x. So this part I can write as 1 over x d2y dt squared. All right. Now from here, I just need to rearrange this algebraically. So I will have, I'm going to multiply both sides by x. So therefore, I will have my second derivative plus x dy dx is equal to d2y dt squared. And then now from equations number 2 here, I knew that x dy dx is actually equal to dy dt. So therefore, this whole second order differential equations can be transformed into plus, hold on, it's not plus. So just let me correct that. I'm going to manipulate this algebraically. So I'm going to bring all this over to the other side here. So therefore, I will have d2y dt square subtract off with x dy dx. And then we know that x dy dx from equation number 2 actually represent dy dt. So therefore, this is what I have, dy dt. All right, so this has been proven. All right, now I hope the first part of this equation, the first part of this problem is clear to all of you. All right, now I'm going to pause here for a while. I'm going to continue on shortly. All right, let's look at the first part of this problem, which is here. Okay, now we have solved the first section of this problem previously. So we managed to show that the first derivative is satisfied by this equation, and then the second derivative is satisfied by the second equation here. Now we are going to transform these second order ordinary differential equations that represent y in the functions of x in this case into another differential equations that involve only t and y. All right. Now how we can do that is quite direct, knowing that we have, okay, so here I'm going to rewrite this one more time, knowing that we have x dy dx is equal to dy dt. Okay, this is number 1. And then we also have proven this. All right, now this is our second equation. Right, we're going to make use of these two equations to transform these second order ordinary differential equations from a y in term of function x into a t in term of function y in this case. Right? Now, what we need to do is just substitute this into the left hand side and right hand side. Knowing that x is given by et also. Yeah, so don't forget this one also. Now we're going to substitute equation 1, 2, 3 onto the left hand side expression and the right hand side expression. So therefore we have 4x squared d2y dx squared, which is represented by this second equation. So that is basically just 4 times second equation, and then plus 16x dy dx. So x dy dx is basically multiplied by first equation, and then finally we have 25y, and then 50 ln x. Now we know that x is e to the power t, so therefore that is e to the power t minus 1. Okay, so from here we have so 4, that will be the same as 4 d2y dt square minus of 4 dy dt plus 16 first equation, so 16 dy dt, okay, from here plus 25y, and then we can simplify the right hand side expression into 50t, right? This is 50t minus 1. So from here, if we try to simplify this, we have d2y dt square here plus 12 dt, 25y equal to 50t minus 1. Now that will be our second order ordinary differential equations that represent y in term of function t here. Okay. Now by letting the solutions to these equations, so we can let y be a lambda t here. All right, once we have make these assumptions to the solutions to this equation here, we will be able to obtain its characteristics equation to these equations number 4. As such, we have the characteristic equations to equations number 4 as lambda square plus 12 lambda, oh yeah, I think I've missed out the 4 here, plus 25 equal to 0. Okay, now from here, if you solve this quadratic equation using the quadratic formula, we will end up with 3 over 2 plus or minus, let me see, that should be a 2i here. All right, and then therefore the complementary functions, just write in short, the complementary functions for these homogeneous equations would be a y. It must be, since this is a complex solutions, so therefore the solutions to this would look something like this: exponential 3 over 2t, a cosine 2t plus b sine 2t here. All right, now that will be our complex solutions to this second order ordinary differential equation. Okay, but anyway, we can transform these trigonometry expressions into this form here. So we can actually write this as r e negative 3 over 2 t sine 2t plus a phi here. Okay. Here where the magnitude r, we can see that the magnitude r itself is given by the square root of a square plus b square, and then the phi would be the tangent inverse of, let me see if I got it right, sine cos. So the cos should be equal to a b. So that would be a divided by b here. Right, now that will be the representations of this trigonometry form in term of sine only, right? Where the r is represented by this, and then the phi is represented by this. Okay, so I hope this section is clear. We managed to find the complementary functions to this second order ordinary differential equation. All right, now I'll continue for the next one shortly. All right, now let's take a look at questions number 3. Find a particular integral of the differential equations in t and y. Now, just for reference, the equations that we have obtained in t and y is given as such. All right. Now, we are going to refer to its non-homogeneous section, which is shown as 50t minus 1 here. Now, for that, we're going to make assumptions about our particular integral here. We will say that since this is a linear equations, we will represent our particular integral as, in this case, we can call that mt plus c, for instance. Right? We know that the first derivative with respect to t is m, and then the second derivative is given as 0. Okay, now by substituting all these derivative into these equations, we will be able to obtain its unknown m and c. Okay, so from this equation here, we have 4, the dy dt is m, and then 25 mt plus a c is equal to 50t minus a 1 here. Right, now let's give that a try. We have 25 mt plus 12m plus 25c here. Now, by using comparisons to the coefficients of the t and the constant itself, we will be able to obtain, in this case, the m equal to a 2 is quite obvious here, whereby the c will be equal to a -1. Okay, just let me try to finalize it to check whether that is correct. So this is 24, -25, c is equal to -1. Okay, now for that we can write down our particular integral in this form. Therefore, our particular integral can be written as 2t minus 1. Now, that is our particular integral for these equations given here. Right. Okay, now let's move on to the last part. Hence, find the general solutions to the differential equations in x and y. Okay, now the general solutions to, I'm going to write down the general solutions to equations number 1 here, which is given here, can be written as, can be written as a combinations between the complementary function and its particular integral. Now the complementary functions that we have is here, which is given by RE sine 2t plus phi, and then plus with its the particular integral, which is 2t minus 1 here. All right. Now that will be in term of y as a function of t, but we need to transform it back to y as a function of x here. Now knowing that x is given by this, okay, so x is given by this, and then therefore we know that t is equal to ln x here. So we are going to substitute this transformation back to equations number 2 here. Now that will lead us to r exponential negative 3 over 2 sine, oh yeah, I forgot that t is actually a ln x here, so just let me correct that. So there should be r e negative 3 over 2t, 3 over 2t, one more time, hold on, I keep making that same mistake. That t is actually a ln x here. Okay, so there's a t sine 2 ln x plus a phi, and then plus 2t, t as a ln, minus 1 there. And then there you have it. If you want to simplify that, we can simplify as, okay, this one can be written as such: x negative 3 over 2 sine ln x square plus phi plus ln x square minus 1, and then furthermore we can simplify this as r x negative 3 over 2 sine, usually I prefer to write the phi in this case in front, okay, like this, or you can leave it as 2 ln x, that is fine. Okay, and for this last one, I prefer to write plus ln x square, or if you prefer, you can write in this form here. And then that conclude our general solutions to this differential equation, where the y can be written in the form of a function x here. So I hope this tutorial has been useful to your learning. All right, now I'll see you guys again. Thank you very much for